Hi, my name is Lasse. I'm a consultant at the Danish Technological Institute. In this course, we'll look at multi-jet fusion and binder jetting. In this course, we'll talk about what binder jetting and multi-jet fusion is. So we'll talk about which pros and cons there are for the technologies, what design possibilities there are, which design guidelines there are, which materials are available, and what you can actually print. We'll look at the health, safety and environment, the printing process, the post-processing, and finally there's some links and references for you to further study. Looking at this overview of 3D printing technologies, we can see there are 7 main categories. One of these is binder jetting. This is subdivided into 2 technologies, binder jetting and multi-jet fusion, which are very similar but a little different. Looking at the ISO standard, you have the material, which can be sand, metal, polymer or ceramic. And the fusion state is chemical reaction bonding. And the material feedstock is liquid and powder together. And the material distribution method is that you have a printhead and you have a powder bed. And the basic aim principle is reactive curing. And the process category is binder jetting. So first let's look at what binder jetting and multi-jet fusion is. Binder jetting in this presentation is abbreviated BJ and multi-jet fusion is abbreviated MJF. The binder jet printer consists of 4 components. You have the material container, and you have an inkjet printhead, and you have a build platform and a sintering furnace. Multi-jet fusion is a little different. You don't have a binder but a fusing agent, and then you have more nozzles and a curing lamp that cures each layer. If we look below at the process flow, first we coat the build platform with powder, then we distribute a bonding agent. For multi-jet fusion, we then cure this bonding agent in each layer, then we lower the platform. Then we recoat with powder and repeat these steps until we have the finished print. Then we unpack the build job, and for binder jetting we need to debind the parts and we also need to sinter the parts. Here we see 2 binder jet printers. One is for sand to the left, where you have a very large build volume, up to 4 meters long, or you can build many parts in the same run. On the right we see a metal printer, which is very large compared to the market within 3D printing. But you have to note that it's difficult to produce very large parts with this technology. So the advantage is that you can print a lot of smaller parts in the same run. Here you see 2 typical printers within the multi-jet fusion technology. On the left you see a printer which is able to print colors, which is useful for prototypes. On the right you see an industrial printer which is able to print functional parts for industrial use. In this video we can see a binder jet printer in action. This type of printer can print in metals, stainless steel, bronze or tungstens for instance. In this video we see a multi-jet fusion printer in action. Notice that this printer distributes the fusing agent in the same run as the curing takes place. This makes the process very fast. Now it's time to look at the pros and cons of the binder jetting and multi-jet fusion technologies. For 3D printing you often distinguish between visual appearance and functionality. And binder jetting and multi-jet fusion excels in both. For the visual appearance you get very smooth surfaces and you don't have the support marks you typically get for other 3D print technologies. Also you can get a full color for the polymer and for the sand. For the functional side, you can get very high strength, both for the plastic and the metals, and the tolerances are very fine for these technologies. The biggest advantage of binder jetting is that you can manufacture parts really fast. This is useful for sand cores and molds. You get high production speed for metal parts. You can take advantage of nesting, as you see on the right. And for multi-jet fusion, you have on-the-fly bonding and no sintering step. So this is even faster than metal binder jetting. I have highlighted the process of binder jetting below. So setting up the printer takes maybe half an hour if you have many parts. And then the printing begins, where each layer doesn't take more than 60 seconds. After printing we have some time-consuming steps, including debinding and sintering. But while these take place, the printer can print again. Another benefit of this technology is that you get very high layer resolution. You get nice surface finish and you get very fine dimensional tolerances. One of the downsides is the debinding and sintering steps which are necessary for binder jetting. So here the metal powder or ceramic powder needs to be debinded and sintered, and these steps are both time and energy consuming. Another downside of the binder jetting technology is that you have very fragile parts. So this is for metals and ceramics. So when the parts are depowdered, they are in this green state. They are a little fragile here, but you can handle them. But when the parts have undergone the debinding step, they are called brown parts. 99% of the binder is gone. Here they are very fragile and you have to handle them very carefully. Another thing that can be considered a disadvantage of this technology is the build envelope size. If you compare binder jetting in metal with laser powder bed fusion in metal, you can see that the build areas are comparable size, but the build height is higher in laser powder bed fusion. This means that you can print bigger parts in laser powder bed fusion, but since you typically don't want to print very big parts in binder jetting, this difference may not be that important. So if you compare multi-jet fusion with SLS, you can see that the surface area are also comparable, but that the build height for SLS is typically much higher. Another downside of metal binder jetting is the mechanical properties. Typically the parts have worse mechanical properties than laser powder bed fusion parts. Below I have compared some of the mechanical properties for the same material, 316 stainless steel, manufactured using the different technologies. We find the reason for the much worse mechanical properties in the bottom row, where we see the density is much lower for the binder jetting parts than in the laser powder bed fusion parts. In the picture we can see a cross-section of a typical 316 bronze infiltrated component. You can see three colors. The black is porosities, the yellow is bronze, and the blue is stainless steel. So this doesn't look anything like a typical cross-section of stainless steel. Looking at the mechanical properties of multi-jet fusion, you typically compare this to SLS. The mechanical properties are very comparable, but you have less materials to choose from in multi-jet fusion. Looking at the colors, in the top right picture we see a multi-jet fusion part. They are typically black-gray when you take them out of the printer. And in the bottom you see a typical SLS part, which is typically white-yellowish. In addition to gray, you can also print in color with multi-jet fusion, but you need a specific printer for this, and only one material is available, and the process is a bit slower. Another downside of binder jetting in metal and ceramics is the powder handling. This is a labor-intensive manual process to remove the powder, and you need a glove box and a powder recycling station. It would be possible to improve this workflow through automation. Another downside of metal binder jetting is in the sintering shrinkage. You get up to 27% shrinkage for some materials, and this shrinkage may not be uniform because you have friction and you have gravity. An advantage of binder jetting is that you have a very wide range of materials. You can print in sandstone and you get a lot of different colors available to you. You can print in silica sand for making molds. You can print in stainless steels, and you can print in carbides, in all kinds of ceramics, and you can even print in inconels. So all the alloys available for metal injection molding are also available for metal binder jetting. If we look at multi-jet fusion, we don't have as many materials available as for SLS, but we have polypropylene, PA12, PA12 with glass beads, PA12 with color, and even TPU, and all these materials satisfy a lot of the industrial needs. Summing up with the pros and cons, we have very fast production speed, we have high layer resolution and surface finish, and we have many different materials available. Looking at the downsides, we have fragile parts, we have powder handling, we have part shrinkage, and we have worse properties compared to metal laser powder bed fusion. Let's look at the design possibilities for binder jetting. You can get smooth internal channels using binder jetting. You typically have a minimum diameter of 1 millimeter, but it depends on the length and design of the channel. Sand casting is one of the most common applications of binder jetting today. It's possible to print elaborate design patterns that are impossible to produce with traditional techniques. Mostly they are made with silica sand. Another possibility is to make light and hollow structures, as you can see below. Another possibility for binder jetting is to create washout tooling for composites. Here you create a sand component which you wrap your carbon fiber around, as you can see in the video to the right. Then you wash out your sand and you have your final carbon fiber component in the end. The minimum diameter for a standard printer is around 0.2 millimeters, but it depends on the printer. Another possibility is to create complex parts. As you can see in the pictures, it's possible to create really intricate designs, both in multi-jet fusion, as you can see on the left, and in metal binder jetting, as you can see on the right. Summing up on the design possibilities, it's possible to make high-resolution components, you can make hollow structures, and also intricate designs. Now it's time to look at the design guidelines. And first we'll look at metal binder jetting. Hobbs has made this design rules for 3D printing overview, and I'll focus on these 4 features: unsupported walls, supports and overhangs, escape holes and tolerances. Looking at the overhangs first, in binder jetting in metal you typically don't use supports, but you have to be careful when you design your parts. We use simulations to predict the deformation during the sintering step. The green pictures are results of a simulation, and the gray pictures are a result of actual sintering parts. In the top you can see a small overhang with no deformation, and in the bottom you can see a large overhang which was straight before sintering, which collapses completely during the sintering stage. Next we have feature size. The minimum feature size of binder jetting is 2 millimeters, but there are some design rules for this that are interesting. To the left you can see an example of a poor design with a thin structure holding a big block in the top. This will get soft during the sintering and the block will drop to the side. In the middle you can see a better design with support for this pin. To the right you can see a more solid pin that's better at holding the block in the top. To the right we have an example of a tensile test specimen where we needed this very thin structure, and then we had to put in support structures around the part. For escape holes and channels, the minimum recommended hole size is 2 times 5 millimeters, so 2 holes of this diameter. The reason for this is that you want to get the powder out. To the left is the worst design with sharp bends, and to the right is the best design with smooth curves. The way you get the powder out is by shaking or tapping the component or blowing with compressed air. If you have a shorter channel, you can have hole diameters less than 5 millimeters. Finally, we have tolerances and unsupported walls. The standard tolerances are plus minus 0.2 millimeters pre-sintering, but it depends on the size of the part. Some features can affect the tolerances in a negative way. Large flat surfaces, thin walls, overhangs and the orientation of the part are all very important to designing for binder jetting in metal. The design guidelines for multi-jet fusion are a little different. Let's look at these. The design guidelines for multi-jet fusion are very similar to those for SLS, but as we can see below, the tolerances are a little finer and the details a little better. I'll focus on connecting and moving parts and escape holes. The design guidelines for escape holes and channels for multi-jet fusion are very similar to those for binder jetting. But because we are dealing with final parts and not green parts, we can use, for instance, piano wires to clean our channels. If we look at connections and moving parts, multi-jet fusion has a slightly better minimum clearance than SLS, which we normally compare it to. This is interesting if you want to make parts with movable elements, as in the example to the right. Summing up on these design guidelines, as a design engineer, you may follow all these design guidelines, but the final part may still prove difficult in the production. So a feedback between the design engineers and the production is often necessary. Let's take a look at some of the materials we can print in. For this technology, we have a wide range of materials available. When you print a sand mold in binder jetting, we have all the typical cast materials available. But if we print purely in a metal in binder jetting, we have a lot of material as well, for instance 316L or copper. We also have a lot of ceramics available, both alumina and carbides. We can also combine the ceramic and metals in a composite, for instance boron carbide with aluminium. For multi-jet fusion, we have a lot of polymers available. We have PA11 and PA12 with additives, and we have polypropylene, and we have TPU and TPA. Now let's look at what we can print with binder jetting. One example is casting of impellers. Here you would print the mold in sand and cast your impeller in your desired material. Another option for binder jetting is tooling in tungsten and M2. In the left picture, only the outer part is 3D printed, where the inner part is machined. In the picture to the right, you can see a component that has been entirely 3D printed with intricate designs for optimized functionality. It's also possible to print regular parts in metal, as you can see in the pictures below. And finally, it's possible to create small intricate parts with a very high level of detail, as you can see in these 3 pictures. Let's look at health, safety and environment. First, let's look at the safety equipment needed for the different technologies. So first, always read the safety data sheet from the specific machine manufacturer. It may vary greatly from machine to machine what is needed. For binder jetting, the grain size of the powders are typically below 50 microns, and for multi-jet fusion, the powders are also typically in the 50 micron range. That means that when you have loose powder flowing around in the air, you need some filters to avoid it going into your airways. Some of the essential equipment needed is glasses, ventilation, masks, gloves and work clothes. When printing with binders and powders, there are some safety aspects to be aware of. Always read the safety data sheets, always use the required safety equipment. You should know that uncured binder is typically classified as hazardous industrial waste. You always have to clean and cure the parts according to the material specification. Powder is not approved for use with food, drink or medical applications on the human body, but printed parts may be used for these applications. However, when you heat this binder or agent, it may change into different materials, different chemicals, which are not approved for food, drink or medical application within the human body. And you have to make sure that they are not present in the final product. Finally, all powders, and especially titanium powder, is flammable and spontaneously combustible. Regarding fire and explosion risk, you always need an ATEX workplace evaluation. It's mandatory in Denmark and must be renewed with changes or minimum every 3rd year. The ATEX workplace evaluation looks into the possibility of explosion when handling powder and other materials. However, binder jetting and multi-jet fusion are less at risk compared to laser powder bed fusion because you don't have a laser as a heat source during printing. In a previous chapter we looked at the printing process. Now we'll look at the other production steps. First, let's look at binder jetting. After you have chosen your parts, you can orient them and then you can nest them. So this is an advantage of binder jetting, where you can combine a lot of parts closely together and increase your production speed. In the picture to the left, you can see all the parts you want to print and the build place in white. In the top right corner, we have nested the parts with a predefined Z-axis orientation, and in the bottom right corner, we have a free orientation of the parts. This may be advantageous if you want to increase your production speed. Next, in the print job preparation, there is the scaling step. So during sintering, the parts contracts due to the powder particles merging and the parts becoming smaller. This shrinkage behavior varies depending on the material used and can be of varying magnitude in all directions. The shrinkage is mostly an issue for large thin surfaces, but too large shrinkage may lead to cracks. Furthermore, during sintering, the parts become soft because you reach typically 85% of the melting temperature. So to the right you can see the original CAD model, and to the right of the right figure you can see the sintering simulation where this part has bent down in the middle. To predict this deformation, and you can pre-deform the part digitally before printing, and simulation software exists to help with these initial predictions. So in the middle of the figure you can see a negative offset geometry that results in a sintered geometry. This process of simulation typically takes several iterations. This will result in a revised offset geometry that will lead to a desired output geometry. But often this has a further iterative fine-tuning process where you print a test batch, you measure and tune your CAD geometry, and you may choose a different setter strategy, which I'll return to later, and you have to repeat this to get satisfactory results. Next, we need to prepare the printer, so we need to add or change powder, and we need to add or change the binder. Then you insert the build chamber and you upload the job to the printer. Next, we have curing. Sand and polymer materials are often fully cured during the printing process, where each layer is cured. But for metal binder jetting, sometimes you need to cure the whole build job after printing. Next, we need to unpack the print job and remove the powder. So for some technologies, for instance sand printing, this involves depowdering table and a suction and compressed air. For metal printing, this typically involves a glove box that is closed and a filtering station. For metal parts, we need infiltration or debinding plus sintering. Debinding removes 99% of the binder and is done in a furnace. Then you have to remove the voids either by sintering or infilling. Zero-G sintering would be nice to have, but it's difficult to obtain, especially since you are not typically printing in outer space. So instead you use ceramic setters to support the overhangs and features during the sintering process. Below you can see some typical temperatures and times for both sintering and infiltration. So first you have the binder burnout process, and then you have a sintering or infiltration step. In the sintering step you typically have 20% shrinkage but a very high density, while in the infiltration step you only have 2% shrinkage, but you also end up with a lower density. There are several ways to optimize the workflow when dealing with metal binder jetting. First, you can minimize the powder and component handling, for instance through automation. Depending on the binder curing, debinding or sintering needs, you typically need 1 to 3 different ovens. In the picture to the right you can see first the printing process. Then you remove the unpacked build jobs from the printer and put them in a curing oven. You can do this with a lot of prints simultaneously. Then you remove all the build jobs from the curing oven and effectively remove all the powder together. Now comes the debinding step, where you remove all the binder from the parts. After debinding, the parts are very fragile, we call them brown parts, because all the binder is gone. So you have to be very delicate when you transfer them to a sintering oven. In the end you have the parts and they are ready for post-processing. Now we'll look at the printing process for multi-jet fusion. After choosing the parts, you place them within your build preparation program. Some parts may have a fixed orientation and some may have a free orientation. The idea here is to optimize the production to get the best performance of the parts and the best performance of the process. In the top right corner we have a predefined z-axis of all the components, and in the bottom right we have a free orientation of all the parts. In this way we can optimize the heat deposited during printing to get the best performance of the machine and the best performance of the final parts. In this nesting process it may be advantageous to create a nesting box, so another part where you enclose the small components in order to avoid that these parts are lost in the unpacking of the print job. After nesting we have a scaling step. This is because we have a shrinkage during printing and we need to predeform the parts to make them slightly bigger when printing to get the desired shape in the end. Powder mixing is an important step of multi-jet fusion. So in this step you mix used powder and fresh powder. Typically you use a ratio of 80% used and 20% fresh powder. The ratio depends on the packing density, that is the percentage of fused powder in the build envelope. The optimal packing density is 5 to 10%, but if you pack it even closer, you cannot reuse as much powder. Now let's have a closer look at the printing process. This is often compared to SLS because you want to have a high throughput of parts. So the time it takes to heat up is typically a little shorter for multi-jet fusion than for SLS. Similarly, the print time is also a little bit shorter for multi-jet fusion than SLS. The real gain of multi-jet fusion is in the cooling step. Here the SLS machine has to cool down some of the time within the machine, while the multi-jet fusion can cool down the whole cooling down time outside the machine. This means that you can print the next build job right after you finish the first build job. And next is the unpacking step, which is similar to SLS. Next is powder removal. So you remove the whole build envelope from the printer and place it in the unpacking station. Here you reclaim the powder using a vacuum system and reuse the powder within this unpacking station. Finally, we have powder removal, where we clean the parts. First we clean it with powder that we blast onto the surface of the parts. Next you can blast it with glass, and in the end we clean them with air to make sure that all the loose powder is gone before the post-processing steps. After the printing steps, there are several post-processing procedures that can be performed before the parts are finished. Some of the processes available are heat treatment, abrasive blasting, deburring, some specialties, and of course quality control. Heat treatment is mostly relevant for metal binder jetting. This is done to optimize the mechanical properties. You can get more ductile microstructures or isotropic microstructures. You can also remove porosities if you use an hot isostatic pressing technology, and you can obtain softening or hardening, and you can improve the corrosion resistance. Abrasive blasting is shared by both multi-jet fusion and binder jetting. Different kinds of media can be applied. Typically corundum beads are used, which have an angular shape. These cut through the surface, or you can use glass beads, which are rounded particles, which even out the surface. In the two pictures in the top right corner, you see corundum particles and below glass beads. In the bottom pictures you can see the as-printed surface of 316L and the glass blasted surface. In the picture to the right you can see that the printing lines have disappeared. Another kind of post-process is deburring, and it's both applicable to multi-jet fusion and binder jetting. You have different kinds of grinding chips for different materials, and it helps to smoothen the outer surface. You should be aware that this technology doesn't improve the channels, small holes and sharp corners. Some special post-processing steps are also available both for multi-jet fusion and binder jetting. You have electropolishing, which you can use to obtain mirror-like surfaces. You have abrasive flow machining, which is especially useful for internal channels. You have PVD coatings, or you can perform vapor condensation finishes, especially for polymer parts. Finally, we have quality control, which is typically an integral part of the production process. Here you often use calipers to test the geometries and make sure that they are within the specifications. But you can also use coordinate measurement machines, CT scanning, mechanical testing, corrosion testing, etc. Everything is also part of typical performance testing within a production setup. Finally, we have some links and references for further study. First, we have some general links for more knowledge on additive manufacturing. And here we have some specific links about binder jetting and multi-jet fusion. That brings us to the end of this course. Thank you for watching.